Hello, I'm here today to talk to you a little bit about an exciting and new invention that could serve as a substitute for an industrial flare. And we're going to talk a little bit about how this thing works. And I'm going to allude to some magic. It's going to appear like this thing is using magic. And I'm going to talk a little bit about our steps to commercialize this idea. But before I do, I'd like to talk briefly about who Carbovate is. So Carbovate Development Corporation was founded in 2018, and like most organizations, we have a fancy, fluffy mission statement, but to boil it away, it all means what can you do with bitumen besides burn it? In other words, bitumen beyond combustion, and of course, I'm talking about Alberta oil sands bitumen. Activities that we have undertaken to that end include doing research on carbon fiber, specifically can you make carbon fiber directly out of oil sands bitumen, but also, and to an even much more sexy product is asphalt. Why asphalt? Well, because oil sands bitumen is, depending on the lease, anywhere between 60 to almost 80% asphalt. And so we developed a process that is essentially, is very energy efficient, much more energy efficient than a conventional E&V unit. And we can configure our process so that it has essentially zero scope 1 and minimal scope 2 emissions. Now, there is a real challenge around zero scope 1 emissions, and that is the flare. A system like this needs to be protected by a flare. And how can you have essentially zero scope 1 emissions if you have a flare? And so to that end, we thought hard about how we could do that, and we've come up with a way to capture and reclaim material that would otherwise be routed to a flare. That has led to 3 patents on this process. So before we go into it in detail, explain how the magic works, I want to just be crystal clear about where this could be applied. This process, the Carbovate FAS or flare alternative system, is well suited for processes handling fluids with boiling points above, say, ambient temperature, say a little bit above, around 30 degrees or higher at atmospheric pressure. It is not well suited for processes that have a high inventory of non-condensables or gases, hydrogen, methane, hydrogen sulfide, that sort of thing. And so the system won't work very well with that. Now, there are ways around that that we could help mitigate the impact of non-condensable content. But for purpose of our discussion, we want to focus on the core idea, which is for protecting equipment containing this type of fluids with boiling points above, say, 30 degrees C. So what are our claims? Well, first of all, we have a patented process, and in certain applications could substitute for a flare. The system is completely passive. When it's ready and in service, the system, as you will see, pretty much can't not work, pardon the double negative, because there are no systems required. It doesn't require steam, electricity, nitrogen, even operator intervention. Unlike a flare, this, as I said already, it captures a material, which once it's captured means it could be reprocessed and sold. There is a containment vessel here, picture as shown in the illustration. This system, without this process, the vessel would have to be large. You'd be thinking something the size of a hockey arena, but because of the fluids that make this thing work, which leads to its magic, this containment vessel can be affordable and practical. The unit could protect a single process or several processes in a large facility, like, say, a refinery. It wouldn't be suitable to protect the entire refinery, but it could protect individual units within a refinery. For companies that are serious about reducing their greenhouse gas emissions, the flare is one of the most difficult emissions to eliminate up until now. And so they would probably, for most people, most organizations will be done by using offsets. So to stand here before you and talk to you about a substitute for a flare is in itself an extraordinary claim. And Carl Sagan famously quipped, extraordinary claims require extraordinary evidence. So what is our evidence? We hired 2 independent, not even in the same country, engineering firms, process engineering companies, and they individually and independently built simulations of our calculations and process idea, and we're able to get the simulations to work without any trouble whatsoever. So we have, in theory, process simulations that show that this would work. To that end, we were able to acquire 3 U.S. patents for this process. those patents were granted earlier this year, and so we're just now beginning to start talking outside of Carbovate about this process. We've since filed three international through the International Patent Cooperation Treaty for international patents, and the IPC has conducted their international bureau review and concluded that these ideas are truly novel, that they're marketable, and that they will work. So how does the Carbovate technology work? What is this magic I keep referring to? So this is a cartoon of the process, and it looks kind of complicated, but we're going to show you just how simple this really is. But before I do, I need to define two fluids. I mentioned that there are operating fluids in here that make this thing work, and are used to keep the containment vessel to within manageable and practical sizes. There is a low vapor pressure fluid involved here, and this low vapor pressure fluid is used to generate the vacuum. And this so what is a low vapor pressure fluid? Well, think of something like motor oil or olive oil, vegetable oil, sewing machine oil. The oils typically have very, very low vapor pressure. And in fact, if you were to throw a match into a cup of motor oil, the match would just go out because there isn't enough vapor being generated by the oil to support combustion. The other fluid we're going and so when I go through this discussion, I'm going to be referring to the low vapor pressure fluid as oil. There's another fluid involved, which creates the head space for the protected equipment fluids. And that low vapor pressure fluid has a significant vapor pressure. Now, it typically boils well above ambient temperature. And we're thinking of something like, say, naphtha, which is camp stove, or isopropyl alcohol, or paint thinner, that sort of thing. So if you were to throw a match in a cup of paint thinner, it will catch fire because there is significant vapor pressure, but it's not boiling. The boiling point is typically 100 degrees C or even higher. So those are the two fluids. So let's strip away all this stuff and show you how simple this thing really is. So here we have our new vessel just offloaded off the truck and ready to be put into service. It's full of air. And so we open some valves which allows oil to flow from storage into the vessel, and liquid fills the vessel right out through the vent at the top over to storage. So now we have displaced all the air. There's nothing in this vessel except oil. We get rid of that. And now we show you the pump section, the bottom of the busier cartoon, and it's going to try to pump oil out of this vessel, but it's completely closed, remember. And so when pump starts, it'll run for a little bit, but it's going to create an incredibly deep vacuum because the oil has, as I said, virtually no vapor pressure. And so what's going to happen is the pump is going to stop running. It's going to cavitate, and it won't be able to pump oil anymore. So we'll have a very deep vacuum here without a vacuum pump, but with a liquid pump. But the limited space for relieved material, because this little bubble here is going to be under deep vacuum. The pump won't run, and we don't have very much space at all for volume to receive relieved material from our protected equipment. So now what we're going to do is we're going to inject the high vapor pressure fluid, or the naphtha. And so when we open the valve and the naphtha flows in, but guess what? Under these conditions, the naphtha is going to flash into a gas because it's at the pressure there. It's well above its boiling point, even though it's only 20 degrees C or whatever inside the vessel. And so what we have is a vapor inside this bubble, which causes the pressure to rise a little bit, which now means our pump can resume operating, and it can continue to pull oil out as naphtha flows in and flashes into a gas. Now, there's a really critically important point to keep in mind here, and that is if you have a hydrocarbon, something like naphtha, and the volume of the naphtha as a gas is 200 to 300 times as high as the volume of the liquid. So when you flash a liquid into a vapor, it occupies a much larger volume. Now we have nothing in this vessel except our naphtha, naphtha vapor. And so as we continue to do that, we end up allowing the pump to remove oil because this stuff is at ambient pressure is well above it, or sorry, temperature, it's well above its boiling point. So it's all in the gas or vapor state. Uh, um, and in fact, the pressure will rise to, so as it is in the vapor state and so what we have now is lots of headspace for our relieved material. And we're still under vacuum. So let's go back to our busy cartoon here. We have what we have now is the carburetor. Instead of it being full of air, as it was shown in the original version, it's now full of naphtha vapor and under vacuum. So this is what we call the armed state, which means we no longer need any of this equipment to be connected except our flare header. And so now we're going to show you a little bit about the magic. How does this work? Recall that this is under vacuum, and we're going to get rid of all of this other. We're going to focus on the relief header and get rid of everything else. And in fact, this can all be completely isolated. The system is now armed and ready to go. The only thing that's preventing flow is our relief valve here. We don't need electricity. We don't need steam. We don't need power of any kind, of compressors, blowers. There's no vacuum pump involved. Nothing is required for this system. It is completely passive. It doesn't even require operator intervention. So now we have our protected equipment and something happens. We have an event causing the pressure to rise, and that'll get the relief valve to open. But instead of going off to a flare, it's going to go through our optional passive relief gas cooler, which is a series of tubes with fins on them. So it's just air coolers. It doesn't require electricity or power or anything to drop the temperature of this material a little bit, allowing it then to enter the vessel. And this is where the magic happens. As this material enters here, recall that 200 liters of gas versus comes from 1 liter of liquid. Well, the reverse is true as well. So as the pressure rises due to this flow, we have our naphtha is going to start to condense. And for every liter of naphtha that condenses, it frees up 200 liters of headspace. Furthermore, because the material that we're protecting here is a condensable material, some of that material also may show up in here and condense and also contribute to this 200 liters of gas or 200 liters of gas that comes from condensing it into 1 liter of liquid. So after the relief event is over, we have all our captured material in here now, plus our naphtha, plus our oil, and the protected equipment pressure is reduced to an acceptable level, which causes our relief valve to close. And that's it. Everything that normally would have been routed to a flare is actually in here and is contained and is completely under control. Now, the magic here, of course, is as the naphtha condenses, what's happening is that the volume tends to be preserved, and also the pressure. So now that we have everything contained in here, how do we recover it? Was very simple. So it's the same as the first slide I showed you on how the system works. You just open the valve, displace everything, included the captured material in the vessel, displace it, and it goes off to storage for reprocessing. And we're now ready. We're now completed the first step of rearming it for service again. So that's how material is recovered. So what I've been describing to you is known as a passive or self-regulating process. It is a passive and a self-regulating process. As the pressure rises, the naphtha condenses, tending to preserve without any intervention at all. It's self-regulating. It does it all by itself. It's just taking advantage of the physical properties of the fluids involved. And that's what we're referring to as applied magic. So where are we with this thing? You may have heard of something called the Valley of Death, where a proponent comes up with a great idea, but it's a long way from being commercial. They're not at all the same thing. So how do we get across the Valley of Death? One of the first things we did, because I recall we have a patented asphalt plant designed to make asphalt cement out of bitumen. And to protect that, we've had our consulting company, engineering company, Thermodesign Engineering out of Edmonton, Alberta, design a actual process unit, a flare alternative system designed to protect the asphalt plant. So what we have are process simulations. We have a capital cost estimate for this thing. We have P&IDs, PFDs, heat material balances, all of the design criteria to build this thing. So that's one step towards commercialization, but it's not commercial. This is still very much in its infancy. We're just now starting to talk about it because we are freed up by having our patents. The Alberta Innovates help fund this thing along with private investors and investment by the Carbovate principles to do this. Now, one of the problems with demonstrating or proving this in a real world application is one of the reasons why we only have simulations is because flares are fundamentally a safety device. They also provide maintenance support services, but at the end of the day, you wouldn't want to disconnect the system from a flare and try this, not without some other evidence besides theoretical simulations that it'll work. So where are we on this trek across the valley of death? We think we're somewhere here. We're just now getting into the valley on our way towards commercialization. And what is our strategy to get across the valley of death? Well, we think we would focus on planned maintenance. Flares, they're fundamentally a safety device, but they're also very important for maintenance of support activities. And that, we think, is the way to do this without presenting undue risk to anybody or equipment. So how would this work? Well, in a normal facility, you might have in a real world facility, I should say, you might have a vessel that's being prepared for maintenance. And so you use the pumps, blowers, compressors, drains, whatever you have to de-inventory the equipment that's scheduled for maintenance as best you can. But at some point, the pumps, blowers, compressors, drains can't get any more out. There's still toxic or hazardous materials in the vessel. And normally, the way that is the next step then would be to put steam to steam out the equipment. So you connect it to a steam line, you open the steam valve, and the system is then routed to flare. So what you have here is a bypass around the relief valve, and what you can do then is what is normally done is you open the relief valve, and what we are going to do is the same thing, except this is not going to go to flare, it's going to go here. So you open the valve, the steam flows through our cooler. Some of it probably will condense there, and it goes into here, and it does exactly the same as it would if it were, say, benzene, toluene, xylene from an operating event. But so the steam is carrying the hazardous material from the vessel, but again, not going to flare, but going here. And so the hazardous material along with the water is in here, is in this vessel. As the water condenses, it forms a puddle at the bottom. The naphtha, as previously, as the pressure rises, will condense, creating lots of volume for the steam and the hazardous material that's coming out of the vessel. And once the system has been determined safe by the safety department and its inspection, it can then be vented to atmosphere to get rid of the steam, and then it's ready for entry. The contaminated water here can then be routed to the wastewater treatment plant for processing. So that's how the system works. And so I want to differentiate here between a Carbovate flare alternative system and a conventional flare. So characteristics of a flare versus the Carbovate FAS. First of all, there are no continuous GHG or chronic GHG emissions because we have no pilot, we have no flame at all. Acute emissions from a flare can be very, very high. Again, doesn't occur with the FAS because everything is captured. Flames, whether it be in a flare or the furnace in your home or your combustion engine in your car, flames are not perfect. And so you produce all kinds of air pollutants like NOx, SOx, particulates, unburned hydrocarbons, VOCs, et cetera. Well, none of that is applicable to the FAS. Flares today are incredibly reliable systems. They're made reliable because of a whole suite of protection devices, active devices that are required to make the system reliable, including pilot, flare igniters, monitoring systems, flame front generator. None of that is required for the flare alternative system because it doesn't have any, it's completely passive. Flares require a steam supply for operation, not so for the carburetor. It doesn't require power. The flares can produce very high temperature, large flames, so resulting in something called an exclusion or radiant zone, not applicable here. The relieved material, nothing is recovered from a flare. Everything is recovered here. Because there's no noise, no smoke, no light, no emissions of any kind, we think that this process would be very friendly to regulators and neighbors. They'd be receptive to this sort of approach. And if that's true, then sorry, the, flaring is a reportable event most of the time, whether it's planned or otherwise. And because we're not flaring, there should be fewer reporting events. Where could this thing work? Well, we talked a little bit about refineries, and I'm not going to go through them all there, but there's a sampling of some of the process units in a refinery that could be applicable to protection by the FAS. Chemicals and beverages like distilleries and alcohol plants could also be protected. One of our consultants is convinced that there's a opportunity here within the pharmaceutical sector. So in summary, Carbovate has come up with an alternative to flare system for some processes. For companies that are concerned or interested in mitigating challenging emissions, one of the more difficult emissions to control would be flares, and this is a path to do that. If your facility is bottlenecked for expansion or further development because of a flare capacity constraint, this might be a way around that. As I mentioned, because there's no flame, no smoke, no light, no noise, we think the stakeholders would be receptive to this type of technology. And if that's true, it should lead to fast track regulatory approvals. So where are we with our development steps? Well, as I said earlier, we just now received our patent, so we're now just starting on our trek in the public domain, and we're looking to partner with a company to work with us to build a lab or pilot scale unit to demonstrate the concept. That means demonstrate it beyond a theoretical. We're looking for a company that probably has global reach and close ties to the petrochemical and petroleum refining industry sectors. We're looking at building a commercial demonstration unit that might be large enough to fit on a trailer so you could test real world units being prepared for maintenance. And we already are engaging with potential investors and regulators. So with that, hope you enjoyed this discussion. And if you have questions or want to talk to us a little more about this, you can contact myself or our CEO, Don Wood, at the email addresses shown. Thank you very much.